Hello students, welcome back. In the previous video, we went through the definition of the linear mappings, and also we had some examples as well. Now let us review those as quickly as possible in an alternative viewpoint before moving on to the next topic. Here's the definition. A map from one vector space to another is called linear if it satisfies these conditions. Number 1, it preserves the addition. Number 2, it preserves the scalar multiplication. And number 3, it preserves the zero vector. The third condition is not really that necessary because you can always plug in c equal to 0. I mean the scalar 0 here, then the third condition pops up. So the third condition by itself is not really necessary, but let's include it anyway for the sake of convenience. Now, have you talked about these kind of things before? About the third condition popping up from the second condition, blah, blah, blah? Yes, we did. I'm talking about these three. Subspace condition, and we have these three. Close on the addition, close on the scalar multiplication, and the zero vector, where this can be deduced by simply plugging c equal to 0 here. And the parallel does not end there. These three can be reduced into a single condition down here, close on the linear combination. Let's go back to the previous notebook. And these three are equivalent to this single condition, preserving the linear combination. In short, the concept of subspaces and the concept of linear mappings are related. And this relation will become really important the next week when we discuss those subspaces generated by linear maps. I'm talking about kernels and images. Anyway, we're going to talk about those next week. And at this moment, the alternative viewpoint is going to be sufficient. Okay, let's go to the examples. And these kind of theoretical examples, I'm not interested in those anymore. Let's come back to this elementary example. So if you have a m by n matrix, then it defines a linear map by matrix multiplication. X and Y are column vectors, and X is n-dimensional, and Y is m-dimensional. Then you can consider a linear map that is sending n dimension to m dimension. These two expressions are equivalent actually. Here we use a little bit strange arrow mark here to represent an element x is being sent to an element y. Here we don't have those strange vertical line there. This one is just usual arrow, and that's for sets. This is the domain, and that's the target. And this kind of subtle distinction is important in analysis. Here in algebra, it's not that important, but let's use those anyway. Whenever I have an element going to another element, I'm going to use this kind of notation. Arrow with those little vertical bar. And if you have set to another set, or vector space to another vector space, then I'm going to use the usual arrow. Okay, all right. So much for those examples, and then let's go over to a little bit more geometrical example. Here's an example. So we're coming back to this one again. You see, this matrix A here happens to be the identity matrix. In that case, what kind of map is this? Well, identity doesn't change anything, so this will be just identity. XY will go to XY, and that's it. No problem there. So basically, I will send XY to itself. That's basically it. It's an identity map. Okay, here's next example. This time, the matrix A is A00B. Okay, what kind of map is this? So L is sending, oops, XY to, let's see, so let's do this matrix multiplication. AX plus 0y, isn't it? And then this one is 0x plus by, isn't it? Did I do this matrix computation correctly? It's just matrix multiplication. Okay, and therefore, this is just AX. Come on. And then just by. What kind of map is this? X is being sent to AX. Say, for example, A is 2, then in horizontal direction, doubled. So stretching by 2. And then if B is, say, for example, 3, then vertically stretched by the factor of 3. It doesn't have to be always stretching. If B is, say, 1/3, then compression by a factor of 1/3. So it's a stretching in one direction and another stretching or compression in the other direction. Well, let's see. Do we have a visualization here? Yeah, okay. This is randomized. This program is randomized. So if I run it again, and I'm going to get different ellipses. So horizontally, let's see, compressed by a factor of 0.04 and vertically stretched by the factor of 1.95, nearly doubled, nearly halved. And let's run it again. And this time, let's see, vertically 1.25, so not that much, but horizontally a little bit more, 1.59 something. So basically it's stretching, so the circle is becoming an ellipse. Okay, all right. Okay, with color coding, it looks really good. All right. Let's go to the next example. So this map sends xy to 0110xy. What kind of map is it? Well, what choice do we have? Let's do the matrix multiplication. F is sending this matrix xy to, see, we are doing elements, so I'm going to use this arrow. And then let's do the matrix multiplication. So 0 times x, so 0x plus 1y. And then down there, 1x plus 0y, isn't it? So it can be simplified into, oh, this is just y, the numerator, or excuse me, not the numerator, what do you call it? The first component is just y, and the second component is x. Oops. We just switched x and y. So what happens if we switch x and y? What kind of map is it? Switching x and y. Is there a good way to visualize it? Well, here's a visualization. It's an inversion, or it's a folding with respect to the diagonal line y equals to x. So here in this picture, we have this kind of graph. And then after taking this inversion, excuse me, there's some alert from this computer. Sorry about that. After taking this inversion, what do you have? Yes. this horizontal direction now became vertical, and then vertical became horizontal. Basically, x-axis going to y-axis, y-axis going to x-axis, x is going to y, y is going to x. That's what the flipping with respect to the diagonal is all about. We have seen these kind of things before a long time ago, I believe, when we are learning what inverse functions, graphs of inverse functions with exponential logarithm, those kind of things. Flipping with respect to the diagonal. Okay, one last example. xy is being sent to cosine theta, negative sine theta, cosine of theta, xy. What kind of map is it? So this xy is being sent to let's see, x cosine of theta minus y sine of theta. And then let's go down, x sine of theta, so x sine of theta plus y cosine of theta. What kind of linear map is it? Does it ring a bell? It'll turn out it's a rotation. Well, this program is randomized, so if you run it again, then you're going to get different angle. Here, rotation with respect to about 1.41 pi, so nearly 270 degrees. So we took that kind of rotation. And then this time, negative 0.75 something. So it's a rotation clockwise. And how do you actually tell this is a rotation? Good question. That's going to be answered in the next section of this notebook. Let's see, do we have enough time for some digression? Maybe or maybe not. If we do have some digression, if you do have some time for digression, then I'm going to bring some notebook from trigonometry class and then have a little bit of discussion there, because we went through rotations and things like those over there. Let's see, how about some 3D geometry? Map P, what kind of map is this? P is sending this XYZ over to let's see, let's do matrix multiplication. X times 1, 0, 0. Okay. And then x times 0, y, 0, okay. And the 0, 0, 0, so it's this one. So XYZ is going to just x comma y. And what kind of map is this? Well, this is 3D, so it's a little bit difficult for me to draw, but it's a projection. You see, you're losing whatever information, whatever height, it just projected down to xy plane. We are just losing this one, losing height. It's a projection. I stopped recording and created a graph. I hope this will help. It's a 3D graph. And XYZ, let's suppose we have those red curve in 3D space. And this map P is sending, basically eliminating Z coordinate down to 0. So this red is going down to blue. And that's the visualization there. We have this red curve on the surface, and then project it downward, and then what do you have? Down here in XY plane, we have a circle, blue circle. Do you see those? Okay, that's a geometrical interpretation of this map. It's a projection. How about the next example? XYZ is going to, this is also interesting. L is going to XYZ2, as L is sending XYZ2. Let's see, let's do matrix multiplication. X, Y, and this one is negative Z. Okay. X and Y stay the same, but Z is going to negative Z. So it's a mirror image. Let me get this same picture and do something about it. Let me stop the recording. Okay, I got it running. Let's run it. And here we go. We have original curve, red one up there. And then this map is sending XYZ to XY negative Z. So X and Y, they coming to you and to the right, they stay the same. But instead of going up, going down, so we end up with blue curve down here. And you can see those circles, red is going down and then just going through this XY plane and mirror imaging. There are too many planes, it's a little bit hard to see. Let me see. Let me change this a little bit. Yeah, let's remove this. Let's remove this one as well. So we have red curve, and then project down, and then to take the mirror image, and then we have the blue curve. So Z is becoming negative Z, so positive Z going down, and we have this mirror image forming. Let me remove the green circle as well. Let's see, where is it? Okay, I don't want that any longer. So there is a XY plane. So with respect to this plane, I am taking the mirror image. So red curve, the blue curve. There's a visualization. The next example, oh boy, this is rotation, 3D rotation. Too complicated, so I'll leave that to you. It's so complicated. It's 3D rotation in row pitch roll. I'll leave that to you.